Okay, so I think we can start. More or less, the participant number are more or less stable. So, welcome everyone to our CMCC webinar. Today, we are glad to have with us Sergio Scanu, from our colleague from CMCC. And he will discuss an important topic related to coastal environmental management. The title is Monitoring Pollution in Coastal Area with a case study of Civitavecchia. So how the webinar will run, it is structured in three parts. I will start with a brief introduction about CMCC. Then I will give the floor to Sergio for his presentation. And finally, the last 10 minutes, we will have a Q&A section where you can ask if you want your question, or if you want, you can share comments on the chat. Okay, so let's start with the brief introduction of CMCC. So the mission of CMCC is to advance our understanding in climate science, improving predictive capability, and drive sustainable solutions to address global challenge in this 21st century, in this rapidly evolving world that we are living in. CMCC is a leading research center dedicated to studying the interaction between climate change and society, to provide reliable scientific results to simulate sustainable growth, to predict environment and develop science driven by adaptation and mitigation policy in this changing climate, society, and economy. CMCC is a non-profit foundation. The center collaborates with a wide network of leading global organizations, research institute, and environment agency, including, for example, IPCC, UNESCO, Columbia University, Princeton Environmental Institute, Mercator Ocean, and so on. Through all these partnerships, CMCC play a key role in climate modeling, oceanographic research, economic resilience strategy, contributing to more sustainable and climate resilient future. Our mission is to use advanced models to create practical solutions, real-world solutions to address global challenge. We focus on advancing climate research through multidisciplinary analysis. We focus on combining climate modeling, impact assessment, and environmental economy, supporting science and drive adaptation and mitigation action. CMCC has a multidisciplinary and transverse approach to climate science that combines first-class climate modeling with impact assessment and environmental economics. Our research infrastructure is a comprehensive system designed to support our mission to climate research innovation. And this is done through 3 multidisciplinary research institutes, 4 strategic programs, a dedicated compute infrastructure supporting advanced modeling simulation, and 2 specialized centers focusing on digital innovation and high-level education training. So let's just focus a little bit in deep on this research infrastructure. So at CMCC, research activities are conducted by several divisions, which belong on 3 main institutes, each with a distinct focus and mission. The first division is the Institute for Earth System Prediction, dedicated to climate modeling and the development of the advanced predictive tool. Then there is the Institute from Climate Resilience, focused on creating data-driven digital model of the Earth system, supporting risk assessment, policy making, and climate resilient development strategy. And then there is the Institute of European Institute of Economics and Environment that investigate sustainable and socially inclusive climate strategy, analyze the intersection of climate, economy, technology, and environmental policy to inform decision-making. About strategic programs, CMCC is driving innovation in climate science through 4 key strategic programs. There is the carbon cycle integration, modeling planetary industrial carbon cycle to support the transition to low emission economy. There is a program called Socio-Economic Impact Prediction, developing integrated model to assess climate change effect on policy, adaptation, and investment strategy. Then there is the global cost as the new frontier, creating a digital twin to analyze coastal dynamic, bringing physical and economic process for better resource planning. And we have put a lot of effort also in AI machine learning climate model that will leveraging data-driven approach in machine learning to enhance climate model and process a huge large scale dataset. Okay, so then at CMCC we have also 3 specialized centers to support our mission to advance climate research and innovation. There is the High Performance Computing Center. We have one of the most advanced computer facility in Europe, full dedicated from climate change research. Then we have the Advanced Digital Innovation Center, a transformative hub that brings cutting-edge technology with the critical research need assuring the digital advancement accelerated climate science. And we have also the Advanced Training Education Center, an important space for education, training, and knowledge exchange on the climate change. Okay, so how to participate to the Q&A session? We will have at the end of the presentation, the last 10 minutes of this session. You should find at the bottom of the screen a small button for asking questions, the Q&A chat. You can type your question in the chat at any time during the presentation or during the discussion, and Sergio will try to answer your question. Okay, so before to start, let me introduce our speaker. Sergio holds a degree in environmental science and a PhD in ecology and management of ecological research from the University of Tuscia. His research focuses on assessing anthropogenic impact of marine environment, studying the effect of pollution on coastal ecosystem, marine litter, and the process of bioaccumulation and biomagnification, and also application of USB type oceanographic instrumentation. He's with us, he's been collaborating with us since more than 5 years, since 2019. And that's it. So I will give the floor to Sergio, that will go to start his presentation. Sergio, you are mute.
Sorry. Good morning, everyone. I'm Sergio Scanu from CMCC GOCO division, and in this webinar we will speak about monitoring pollution in coastal areas with some results of a case study of the Civitavecchia coastal zone, with particular focus on the sedimentary environment. Please excuse me my emotional state, but this is my first webinar from CMCC. The table of contents is divided into 4 elements. In the first, we speak about the general principles of the contaminability of marine sedimentary environment, in which we will see in short the sources and contaminants of the coastal pollution. We will define the first depositional front and areas of greatest accumulation of persistent pollutants. And we will see some elements that define why sediments are important for monitoring coastal pollution. In the second part, we will see some methods for monitoring sediments pollution in coastal zones with some details about the geochronological measurements techniques, some ways to measure background levels of pollutants with the application of some indexes of pollution. In the third part, we will see a case study result for the Civitavecchia coastal area with mass accumulation rate assessment, with some results about the temporal and spatial distribution of trace metals in the Civitavecchia coastal area, and the application also of a bioindicator, that is the use of sea urchin Paracentrotus lividus for assessing bioaccumulation. And in the last part, we will see some application perspectives, in particular connected to the currently ongoing project Renovate, that is applied in the Civitavecchia coastal area and that is coordinated by CMCC, and in which we are working to find some insight about integrating this type of data in the numerical modeling part towards, let's say, the development of the prototype of the digital twin of the ocean that is foreseen in the project. So about the sources and contaminants of coastal pollution, obviously, the pollution in the coastal areas is dependent on the sources type and contaminants type. For the sources type, we can distinguish two main types. One is the point source type, and the second is the non-point sources, such as, for example, urban areas or wastewater treatment plants or factories or agriculture. For the analysis of the main sources of marine pollution weight in the overall pollution of coastal areas, we can see...
Sorry, Sergio, are you share your presentation? Because actually we see you, we cannot see your presentation.
Yeah, I'm sharing.
Okay. Because in the main windows I see you, I cannot see your presentation. I don't know. Try to disconnect to share again, because actually I cannot see. So.
Okay, I'll try again.
Try again, yeah. Okay, now I can see the presentation.
Do you see that?
Now, yes, yeah.
Okay, so, I don't know if I restart from the table of contents, I don't know, or no, I was speaking about this part.
Yeah, this is good, start from here.
Yeah.
Yeah.
So we were saying that the analysis of the main sources of marine pollution is due mainly to 77% by runoff and point source emissions and plus air pollution, with a less weight of marine oil gas production dumping ships. For the types of contaminants, there is this short classification. For example, nitrogen phosphorus pollution from agriculture, sewage, urban industrial runoff, or the chemical pollution with particular reference to persistent pollutants that comprises but is not limited to pesticides, petroleum, pharmaceuticals, and personal care products, heavy metals, industrial discharge. There is also the part related to the plastic debris pollution, and then there is also an anthropic impact, not directly connected with the chemical origin, that is the the direct impact on benthic communities due to siltation. That is, in short, defined by qualitative and quantitative variations in sediment accumulation rates. In this map, we can see a distribution of the concentration of the anthropogenic isotope cesium-137 in the coastal zone that is in the physiographic unit between Monte Argentario and Capolinaro. That is the physiographic unit in which there is the Civitavecchia coastal area. This map is based on the works done by Aldo Brondi at Enea in the late 70s. And this then modified by Aldo Brondi and Professor Marco Marcelli of Tuscia University. We obtained this map, showing three different zonation, the concentration of the isotope cesium-137. This isotope is an anthropogenic isotope that derives from started to appear on Earth in the 50s with the atomic bomb tests. In the years, these thousands of tests created, let's say, some sort of sphere or cesium in the atmosphere that then is subject to fallout processes. In the fallout processes, the cesium return to the sea surface or on the river basins. Then it has affinity and connect with the fine particles on the river basins, and is distributed in the coastal zones by the dynamic. In this map, we can see our principal approach in studying the pollution in the sedimentary environment, that is the identification of the main, the area of the greatest accumulation of persistent pollutants that has the same behavior as the cesium 137, let's say, that has ionic properties, so affinity with fine particles, with identification of the red zone, the zone 2, with the highest concentration at the first deposition upfront from the pollution that is coming from this coastline of a physiographic unit. This is the same process with a river runoff, from which we can identify two main components, the continental and the marine components, that let us to identify the main characteristics for the continental part, that are the lead morphology and geochemistry, and the processes of the continental part, that are the sedimentary and geochemical productivity, and the fine particles association with contaminant, also with the transport processes. For the characteristics of the marine environment, we have obviously the bathymetry and the hydrodynamics, so waves plus the general circulation, and for processes, the fine particle distribution. Based on this approach, we can identify the reason why sediments are important in the monitoring of coastal pollution. For example, fine sediments, mainly silt and clay, capture more pollutants compared to coarse sediments because of the larger specific surface area. They have higher percentage of organic materials, and they have a slower deposition rate with aggregation properties. The sediment environment acts also as a natural archive of coastal processes because of sediment accumulation that keep track of past events that can give us indication of anthropogenic impact. All these features can be also assessed in conjunction with the interaction with biota, so analyzing bioaccumulation, biomagnification processes. The other important element is constituted by qualitative and quantitative variation in fluvial solid transport that are due to, in general, anthropogenic intervention of watersheds, but also to climate change that induce frequency variation in variation intensity of extreme events that led to direct impact on benthic biocenosis through siltation and burial effects. In the graph on the center, we can see as an example the evolution of the solid transport of the Tiber River from the 1932 to the 2020. We can see a decrease of about 500% in 88 years of the suspended solid transport of the Tiber River. About the methods, they are connected with the zonation we have seen in the cesium map. We can say that a simple grab, or in this figure there is shown a Van Veen grab, can be used in zone 1, 2, and 3 to obtain spatial distribution of sediments and after analysis of contaminants. We can use a gravity corer or in general corer for the zone 2 to obtain temporal distribution of sediments and contaminants using geochronological techniques. And we can use sediment trap, in particular for the zone 1 that is characterized mainly by sandy sediments, to obtain spatial and temporal in the short-term distribution of sediments and contaminants. For the analysis, at least in Civitavecchia case, we use ECP-MS for the analysis of trace metals and gamma spectrometry for geochronology. About geochronology, the geochronology approach we use is based on the analysis of the activity concentration of the isotope, that is a natural isotope lead-210. That means that we obtain in a core an exponential trend of concentration starting from the bottom to the surface of the core. This exponential curve is constituted mainly by two elements. The first is the so-called supported lead-210 that is connected with the decay chain of the lead-210 that belongs to the decay chain of the uranium-238 that happens in the earth crust and in the soil. A part of this decay chain passed through the creation of radon-222, that is a gas. A part of this radon can escape the soil and the earth crust, so is emitted to the atmosphere, then decay to lead in the atmosphere, and the lead-210 is subject to the same process we have seen for the cesium, so it is subject to fallout processes. That so the lead falls on the sea surface or on the river basin is associated with fine particles. This part of the process is the part of the exponential curve that is called unsupported lead-210, and that can lead us to measure, in short, the amount of sediment that accumulate in a surface area of the bottom of the sea. The measurement of the lead-210 is performed through gamma spectrometer using the decay equation, in which we know the number of the atoms of the lead at a present time and the number of the atom at a time zero. Then using the decay constant of the lead that is based on the lead-210 half-life, that is 22.3 years, we can obtain two main measurements. The first is obviously the dating on the sediment core sections that can be then further analyzed to obtain the temporal trend of the contaminants in the sections. And the second important information is the measurement of the mass accumulation rate, that is the mass of sediment that accumulate in a surface, that is obtainable through the application of some interpretation models. Then for the methods, we can also use background values calculation for persistent pollutants, in particular for trace elements. The definition of background values is that they are the natural concentration of elements or compounds in the environment that are unaffected by human activities. The identification of background levels for a pollutant can be done using areas with minimal human impact, so through superficial sampling, or using historical data before industrialization, so reaching, let's say, pre-industrial section of a core through sediment cores in which we can see what the level of contamination in pre-industrial periods. Then we can also assess the pollution through the application of a series of indexes. We applied some of these indexes, in particular the enrichment factor, that assess the degree of contamination of sediments, comparing the concentration we obtain with a concentration of a reference material. Again, this reference material can be from areas of minimal impact from human activity or from historical data, or also, as in our case, with a table of element abundances in various major units of the Earth's crust, such as the Turecian and wettable work. The potential toxicity response instead is more oriented towards the effect on biota, and it is a cumulative index. So we have one index for the cumulative effect of all the trace elements of persistent pollutants that we are analyzed, and this based on the toxicity factor for each of these elements we have analyzed. So now we will see some of the results about this type of approach and studies for the Civitavecchia coastal area. The Civitavecchia coastal area is characterized by the presence of three main river basins in the northern part, starting from the north, the Fiora River, the Marta River, and the Mignone River. And then there is a minor basin that is called Marangone Stream that is south of the port of Civitavecchia. Civitavecchia was characterized after the end of the World War II by high industrial activities. In particular, it is present now an energy production hub that is constituted by the presence of two power plants. One of these power plants is a coal-fired power plant that use about 4 million tons of coal per year. Then there is an important port that is called Port of Rome, that is one of the most important ports for cruise traffic in the Mediterranean Sea, with more than 3 million passengers per year from cruise traffic and intense maritime traffic. There is the urban area that is characterized by a population of 60,000 people. And there is a context, a particular geological context characterized by some geochemical anomalies, in particular of mercury and arsenic, deriving from the presence of mines, of past mines activities. One is on the north toward the Fiora, that is the complex of the Montamiata complex, that had the mines for the production of mercury, starting from the processing of the cinnabar mineral. And then there is another geochemical anomaly to the south towards Capolinaro in the Tolfa Cerite complex that is characterized by abandoned mines of marcasite, pyrite, and galena. This is an example of the results we can obtain through the mass accumulation rate assessment. In the past years, we collected a total of 5 cores in this area, one in front of each of the regional basins, and one in front of the structure of the port, and one in front of the stream Marangone. Here we see the values, the trend of the values of the mass accumulation rate in 2 cores. One is in the Marta River core, and the other is in the Mignone River core. For the Marta River core, we managed to detect the signal of a flooding event that happened, for example, in May 2004, with another flooding event in November 2005. It is indicated by the maximum of the mass accumulation rate in this time horizon. For the Mignone River, we have quite a constant evolution of the mass accumulation rate with an increase starting early in the 2000s of about 50%. The accumulation rate assessment allowed us also to define the mean values for these basins that are reported in the table. Using this assessment, we calculated the total pelitic sediment flux in the zone 2, so characterized by pelitic sediment, that amount about 860,000 tons of pelitic sediment here for this area. And we compared also with another study that was performed before our work, that is quite similar in the quantification, but this was based on a totally different approach with, for example, direct measurements of suspended solid transport and bedrock transport in the same river basins, coupled with a hydrological technique that is based on iso-erosion curves. This is an example of the same course as before for what we can obtain from the analysis of each of the sections of the core for example, the concentration of trace metals we can see that for these cores, we have quite a constant evolution of the concentration of these of the arsenic, for example, for the Marta core, with a slight decrease for the mercury for the same core, with the same pattern of decrease for the mercury for the Mignone core, with instead an increase, quite evident increase in the concentration of the arsenic, starting again early in the 2000s, in a time span of about 40 years. These are examples of the results of the superficial sediment analysis that are based on more or less 26 stations of superficial sampling. We show here 3 metals that show a totally different pattern in the distribution of the contaminants in the coastal environment. We can see that for arsenic and mercury, we have 3 hotspots of high concentration in the coastal zone, in particular towards the Fiora River, so connected to the Montamiata complex, in the correspondence of the Mignone River mouth, and also in correspondence of the Marangone stream mouth south of the port of Civitavecchia, while, for example, the lead has a totally different pattern that show higher concentration towards the offshore areas with lower concentration near the coastline. This is the application of the same indexes we have mentioned before that show high level of enrichment factor for arsenic and mercury for this area with correspondence with the hotspot we have identified in the superficial sediment analysis, with instead lower or the absence of enrichment for lead and nickel element. We have also assessed the potential toxicity response for the area, and we obtained the value of high potential toxicity response for the metals, in particular for the area south of the port of Civitavecchia that is in front of the mouth of the Marangone stream. Then we applied also, we tried to assess the effect through bioaccumulation processes in the biota using the sea urchin Paracentrotus lividus as a bioindicator. So adding, let's say, another layer of complexity in the study of the coastal area. The area of the coastal area of Civitavecchia is characterized by the presence of 4 sites of community importance, with Posidonia oceanic habitat on various substrate, and the presence also of coralligenous habitat with different areas of value. The total extension of the Posidonia meadows in this area alone is approximately 1,070 hectares. We use the Paracentrotus lividus as it is considered a keystone species, and it is a grazer for the coastal zone, and it has limited mobility also. These are the results that are completely in agreement with the study we made for the metals in the superficial sediments. The results show that we have the maximum of the concentration of arsenic in correspondence of the hotspots we have identified through the indexes, through the analysis of the metals in the sediments for the arsenic, while, for example, for the lead, we have a totally different pattern that seems to indicate a different contamination deriving probably mainly from the urban areas, from the port activities. About the application perspective of this type of data, we are currently working at the Renovate project that use some of this approach in its activities. The Renovate project is a long-term project to develop ecosystemic approach applied to compensation, mitigation, action in coastal marine environment. In this project, we have replicated some months ago the bioindicator approach using again the switching to make a comparison, but we are working on the results actually. The objectives of the project are, in short, environmental compensation action for Posidonia oceanica and coralligenous habitat toward ecosystem services restoration, the development of an early warning system for extreme natural events, the dredging and pollution impact prevention, the development of a prototype of digital twin of the ocean for marine ecosystem restoration and nature-based solution implementation plan. And it has a partnership that has the CMCC as a coordinator, 5 universities, such as Tuscia University, Palermo University, Milan, Bologna, and so on. OGS, CNR, also with the involvement of local fishery, divers, and citizen science. This project involved more than 40 researchers and has a timing of 10 years. The main pillars of the project are the application of nature-based solution for the compensation of the potential impact that the work of the enhancement of infrastructure of the port of Civitavecchia can induce. And also is based on another pillar that is the application of models. So the development of numerical model system for the area that can include a series of scenario simulation, and also a development of an operational model that is shown in the figure on the right. This to support, for example, the position and sizing of compensation measures that are foreseen by the project, such as eco-sustainable moorings, barriers, or anti-throttling deterrents. Also, with the reduction of uncertainty when selecting areas for restoration, so in the application of the nature-based solution that are the reintroduction, in this case, of Posidonia oceanica and coralligeno, also based on bycatch recovery, and also to consider in the model the effect of climate change on marine coastal ecosystems. This is a scheme that shows how we plan to work toward the new insight to develop a prototype of the digital twin of the ocean, in which I highlight some of the main elements in which the study of the sedimentary environment can be involved to add the complexity insight through numerical modeling. For example, we are actually applying USV surveys that give us a detailed map of Posidonia oceanica with canopy 8% of coverage, and also some indication about seasonal variation of the meadows. This can be used, and this is used because there is a paper that I know that there is a paper with the colleagues of CMCC at Tuscia University that are actually studying the interaction of these detailed Posidonia oceanica meadows maps with the hydrodynamic fields, in particular with the wave, and this can be further enhanced as the possibility of investigation for the area, including, for example, some of the approach we have seen for the sedimentary environment, such as the mass accumulation rate or the suspension processes to obtain, for example, the pollution distribution maps that are more detailed. This is a detailed description of what is the USV application. In our case, we use to obtain detailed Posidonia oceanica maps that have 8 coverage percentage indication using a USV EcoBot equipped with aquatic habitat ecosounder. That this type of maps can be coupled with a numerical modeling approach. And we could also add some other features in this, studying, for example, the utility of giving a boundary condition that consider mass accumulation rate in the area or sedimentation and resuspension processes in connection with the variation of the hydrodynamic field with the detailed map of the Posidonia oceanica meadows, with the potential outcomes to have, for example, of persistent pollutant fluxes simulation of scenarios with detailed distribution for spot identification, and also to give us some insight about the interaction with benthic biogenosis. Thank you very much.
Okay, super. So very important study. So important to track and mitigate pollution in the coastal area like Civitavecchia. So let's see if there are some questions. Okay, question answer. Yes. So there is Asciniotta is asking, what is the dispersion spreading of the contaminant due to? So which are the factor contribute to dispersion spreading? And he's also asking, does the model take only the river discharge and is spreading in the coastal region? And also, he leave a comment. He said that I assume tidal circulation along shore current induced by wave will be also important for this kind of study. So,
yes, I can say that, as I said before, there is a paper that will be published in short. I'm not the author, but among the authors, but I know that my colleagues at CMCC and some colleagues of Tuscia University are studying this at the first approach for the interaction between the Posidonia oceanic amidos and the waves.
mm-hmm.
So a further step could be adding this hydrodynamic evolution using modeling scenarios with, as I said, boundary condition that we have studied for the area, adding, for example, the fluxes of sediments, and so considering the river solid transport in the model, and adding the let's say, evaluation of the amounts of the sum of the pollutants. In that case, are persistent pollutants associated with fine particles. So there is the aim is to consider this in the with waves and consider the waves. It is currently the study is currently going on in an hydrodynamic way, let's say, for now.
Okay, so thanks. Then Svitlana, she's asking, what's about hydrocarbons, CS137, microplastic in sediment cores?
Okay, for the cesium, I have not shown in the examples of the results, but we have a core analyzed with the cesium-137 that was one of the 5 that we have collected in the years, and this is the one in front of the southern part in the Marangone stream. And we detected the start increase of the cesium for the 50s era, that the core managed to reach the year 1940. But failed to detect the Chernobyl accident. Mm-hmm. So we had a partial alignment of the temporal trend, but we have analyzed in that core. For the microplastic, my colleagues also at CMCC, for example, Daniela Pezzolla, started to study this, and we analyzed in the superficial sediments in biota. Would be really interesting to analyze also the evolution of microplastic in sediment core, because there could be also a variation in the plastic type, you know, or not only the quantity, but we could also categorize, let's say, the sources of the types of the microplastic in the course, but also understanding see if there is a variation in the types of plastic in the course. This is a really interesting topic, yes.
Interesting, also complex.
Yeah, yes.
Then Giovanni Coppini is asking, okay, it's very interesting that you mentioned that some of the pollutant may came also from industrial, urban, and port activity. Maybe it could be interesting to understand through high-resolution atmospheric model if pollute atmospheric dispersion may be the driver of this contamination. What do you think about this?
Okay, I totally agree. I also add that we made another study with in which we have the results of electronic microscope analysis of what is falling, let's say, on the top of the roof of the laboratory in the port of Civitavecchia, from which we managed to have a classification of different sources. For example, there are also microparticles from the coal. There is an important power plant near the port also, and can be also can be done a distinction between these types of particles from the atmosphere. But for sure it will be interesting to understand high resolution through our high resolution modeling if the dispersion might be the driver of the contamination. Yeah, because also this is one point that it's really complex to understand, at least in the context of Civitavecchia, because as said in the presentation, we have two geochemical anomalies, one on the north and one on the south, and related to mercury and arsenic, for example. And the tracer, the main tracer in literature for the co-combustion are mercury and arsenic. So we have some sort of overlap between the contribution, and it's difficult then to quantify. I think that this approach could be really interesting also for the consideration of the potential impact that can have also the port that is with 3 million passengers per year, high traffic, maritime traffic. It's for sure an important source of pollution for the area.
Okay, super. Okay, so next question by Gloria Mozzi. So can this modeling approach be used to study transport plastic, microplastic, and potentially degradation to microplastic?
Okay, I think I have not so much knowledge about modeling in this sense.
Mm-hmm.
But reading macroplastic, I think that can be done yes. And I don't know if it can be done the degradation. Probably yes. But it could be interesting to see this, yes.
Yeah, another tracer to model. Yeah. Svitlana replied to your answer and with another question. Do you see the trace of Chernobyl disaster in your CS 135 data?
As I said, no. We have only one core with cesium 137, and the Chernobyl signal is absent, but we have the signal of the bomb tests in the 50s.
Okay. Yeah, Svitlana. Okay. Then Gopal, very important subject. What is the probable solutions? Very generic question.
Yeah. Okay. We can split this probably in two parts. For example, for the variation in the sediment accumulation that can lead to burial effects. So the solution is to face the climate change, and that must be coupled with activities of maintenance of hydrographic basins. For the pollutants, the solution is to start to not burn coal, I would say. And in our context, it could be also useful to have maintenance of abandoned mines. Because, okay, we have geochemical anomalies that is natural, but these mines are abandoned. So we have minerals waste such as cinnabar, galena, marcasite, and so on. And the fact that they are abandoned means that the river runoff enrich the solid transport with these elements because there are remains of the mining activity in the hydrographic basins. But I know, for example, that Civitavecchia is the coal-fired power plant of Civitavecchia is dismissing, and so the coal combustion will be abandoned, and this is a good news about this. To say the truth.
Perfect. Okay, so there are no answer. Gloria is very happy for your reply. Okay, very interesting. And yeah, I think we are almost 13. So super. So thank you very much for attending this webinar. For all your participants, you are a lot, more than 60. Thank you, Sergio, for the
Thank
presentation.
you to you for moderating this. Thank you for all the people that listened to my presentation. Thank you very much.
Super. Bene. Bye bye.
Goodbye. Thank you.